Hi everybody, this is Nafish. Today we are going to work on multiple signal classification in short music, and we are going to see if we have multiple targets closely spaced, if this algorithm can resolve those targets. Resolving means finding those angles, okay? So just giving you an example right here. So let's say we have two closely spaced cars, okay? And we have a target vehicle that is trying to measure the angle of arrival of these two cars, okay? So since they're closely spaced, the conventional beamforming or the fast Fourier transform technique might not be able to find the angle of arrival. So that's why we need one of the super resolution technique, and I'm using music here, okay? And we're going to have two targets, okay? So before we get started, here is the Wikipedia page for this algorithm, and you can see how finer those peaks are, okay? So the finer the peaks, or if we have some super resolution, then it will be easy to distinguish two closely spaced object, okay? And basically we will be trying to implement this equation right here for multiple targets, okay? In the previous chapter we used one target. Now we are going to use two targets, okay? These equations little bit looks little scary right now, but I believe, like, when we are going to implement in Python, it will look very easy, okay? So let's get started. First of all, the workflow, okay? So basically we are going to have two transmit antennas and four receive antennas, so basically my MIMO system, okay? And we are going to generate two targets with different angles, okay? So here in this portion we are going to ask the question to music, like, hey, what is the angle of arrival, can you find that out? And then in the music algorithm there are the steps. So from the received signal we are going to measure the covariance matrix. Then from the covariance matrix we need to calculate the eigenvalues and eigenvectors. And the third step will be, we need to separate the noise and signal from the eigenvectors, okay? So you can see, like, we will have two targets. So basically we'll have two signal component and two noise component, basically, because we are using four receive antennas, right? And then the last step is going to be implementing the equation I showed you in the Wikipedia page, okay? So let's get started. First thing first, we have to create two transmit signals, right? So we all know, let's say tx1, we have amplitude, and then we have exponent, and let's say we have np dot pi, then frequency component and time vector, okay? So this is a sinusoidal wave equation, and I'm going to copy it and paste it again, because we are going to have two transmit signal, right, coming from two different transmitter antennas, right? So tx2, just changing the frequency here, right here, okay? And I'm keeping the amplitude same for both signal, normalized amplitude, but we'll change it later and we'll see how that impacts the music algorithm, okay? So let's say f1 is 1 gigs, and then f2 is nothing but half of this frequency, and we have samples of, let's say, 5,000 samples. So, and we also need to define the sampling frequency, fs. Let's say it's 10 times of the f1 frequency component, okay? And then need to have the time vector, and we can derive that. So np dot a range, we need to give this number of samples, and that's going to be divided by the sampling frequency. So I think all of the variables right here in these equations is already defined, okay? So just going to plot it out real quick. So plt dot plot, and then let's look into the first 100 samples. So, and look into the transmitter one, okay? And I believe we have to take real part, because this is a complex number, right? Since we have an imaginary component here, right? So let's run and look into the sinusoidal wave. Here it is. Now this transmitter is going to hit the cars, right, we showed. So the transmitter is going to hit these two objects, and we are going to get a receive signal. So we are going to simulate the receive signals right now, and we are going to have two responses, one for tx1 and one for tx2, okay? And the way we the equation we have here for the receive signal is we need to have the steering vector, and that's going to be multiplied by the transmit signal. So tx1 steering vector s1 and steering vector s2 multiplied by the transmit signal tx2, okay? Now what is this steering vector? I'm just going to give some very high level overview. So let's say we have four receive antennas, right? So rx0, then there's a physical separation to rx1, right? And the distance is d. So basically these two antennas are separated by a distance d, okay? So then rx2 d, and then rx3. So you can see the antennas are physically separated, and that's why we are not going to get the transmit signal impinging on the receiver at the same time. There will be a phase delay, or so you think it as of a filter, okay? So there will be a filter response applied to these transmit signals, okay? And assuming it's a lossless environment, so there is no loss. Whatever amplitude we are sending, we are going to receive the same thing. Okay, so the responses of this delay or the weights is going to be incorporated in this S1 and S2, which is the steering vector. Okay, so let's define those two. So we have S1, and basically this is, I will just copy this part, the transmit signal we are sending out. Okay, and we have 4 receive, right? So we have to make some changes here. First of all, we have to introduce a negative sign, because the receive signal is having the reverse direction of the transmit signal, right? And then what else? I think we have to have d, the distance here I just showed. Okay, and then which component we're looking at. So this is for the first element 0, and then what angle. Okay, so np dot sign, and then let's say I haven't defined the angles, so let's say the angle of the target are angle 1 is 10 degrees, and angle 2 this is, let's say, 20 degrees. So since this is exponential right here, so we have to convert this into radians, right? So angle 1 in radian, this is nothing but we have this angle, then multiplied by np dot pi divided by 180. Okay, so copying this part and pasting it down here. So this is angle 2 and changing the angle here. So again, we have two targets and they are having different angles, right? So they are located at different angular position compared to the radar. Okay, so now we have to incorporate this angle here in this receive signal. Okay, so angle radian 1. Okay, so this is what we have for the first element. So we have to copy this 3 more time. Okay, because we have total 4 antenna elements. So 1, 2, and 3. Okay, we have to change the antenna element. So this is the first element, that was 0, right? Then we have to have 1 here for the second element, then 2 right here, and lastly we have to have 3 here. Okay, so this is the weights for the target that is coming from angle 10 degree. Okay, now we are going to paste it right here again, and this is steering vector 2. Okay, S2. Now we have to change, only thing we have to change here is the angle here, right? Because this is for a different angle, so the weights will be different. Okay, and keep in mind that the music algorithm doesn't know how many targets we have and what are the angles of arrivals. Okay, so basically this is a signal we are creating, and then the music algorithm needs to figure out two things: how many targets we have and what are the angle. Okay, these are the two angles like we can see, but the algorithm needs to find it out. Okay, so this is a question we're asking to the algorithm. We'll be asking it. Okay, so one thing we have to introduce here is we need to have a transpose right here. This is for mathematical necessity, because when you are doing the matrix multiplication, you need to have the number of columns of the first matrix and number of column of the second number of rows of the second matrix needs to be equal, right, for any matrix multiplication. So that's why we need that. And a couple more things. One is, so this is a list. If you look into the type, this is a list, so we have to convert it into numpy array. Okay, so just keeping the same variable name but converting it to numpy array, and this is also for mathematical necessity. Okay, so the input is S1, copying this thing again and pasting it right here, converting this S2 to numpy array and pasting it here, because this tx1, that is also a list, so converting that into array, oops, and tx2. So now we are all set for the matrix multiplication. Okay, so we have it here, right here, and then so these are two separate responses, right? One for tx1 and one for tx2. So the combined receive signal will look like, we're just going to add it, right? So rx for tx1 and rx for tx2. This is the combined response, and let's have a plot. ELT.plot, and then we have the time vector plotting the first 100 samples, and then np.real, taking the real value of this receive signal. Okay, and this is, let's say, the first element. Okay, and 100 samples of the first element. Okay, so let's copy and paste it 3 more times, because we want to see the other 3 components as well. Okay, so this is second component, third, and fourth. So let's plot it out. Okay, the distance d here is not defined. Usually the distance d is 0.5, and there are some we usually use this number because there could be, like, if we have more or less, there could be some creating loads. Okay, so just trying to check out if there is any mistake I have on. So now we are going to run the music algorithm. Okay, so we need to figure out how many targets we have. Okay, and also what are the angles of those targets, and we are going to use this music algo right here. Okay, so the first step is we have to calculate the covariance matrix. So let's say define the variable RxS, which is the covariance matrix, np dot, it's a built-in function in NumPy, and we are passing this receive signal right here. And let's also plot out the real values. Okay, so np dot real of this covariance matrix. Okay, and you can see, look into the diagonal components, more or less same. Okay, so basically this matrix is showing the relationship, okay, of the antenna array elements. Okay, so this is the first element, and how this is and this cross elements right here, it's showing like how it is related to the other antenna elements. Okay, so the first step is to calculate the covariance matrix from the received signal. Okay, now the second step is to calculate eigen values and eigen vectors. Okay, so here also we'll use the built-in function in NumPy. Let's say two variables, eigenvalues and eigenvectors. So e values and e vectors. Okay, so these are the two things we will figure out from np dot linear algebra lin alg right here dot eig, and we need to pass this covariance matrix Rxx. Okay, and then let's plot out np dot real values of eigen values. Okay, so this is the eigenvalue right here. It's kind of little hard to explain, but I'll just plot it out. So np dot let's say plt dot plot, we have this, and then let's plot it out and look into the values. Okay, so this is the eigenvalue. You can see, like, the signal will be higher than the noise. Okay, so basically we can see one signal component right here, one is right here, and this two is probably noise. Okay, but to find out distinguish between signal and noise, we need to have a threshold, and then we need to run some algo, like say, hey, above this threshold it's signal, and below that threshold is noise. Usually I already opened it, like AIC and BIC algos, to find out what is the number of signal and noise. However, that's kind of complex, and will take some more time, so I will discuss that in later lecture probably. I'm just going to use a different technique here, which is like taking the median of these four values right here. Okay, so np dot median, and then passing these eigenvalues. Okay, and let's say this is our threshold. Okay, so this is our threshold. We are calculating a threshold from the median values of these eigen values. Okay, and then we are going to pass a condition here. Okay, the condition will be like, anything above that signal threshold value will be signal, and then below that threshold is noise. Okay, so number of signals, let's say n signals, is nothing but np dot real. Okay, then we need to take this eigen values, and it's greater than this threshold. Okay, so anything above the threshold, signal. Okay, and it's going to give us like true or false, right? So we need to do another calculation, which is np dot count non-zero. So basically this is just going to calculate how many true and falses we have. Okay, and let's show the signal, how many signals we have gotten. So we got two signals. Okay, and which is in fact the case. Okay, so the algorithm was able to find out we have two signals. Okay, and we have basically from here, next thing we need to do is separate the signal and noise. So separate the signal and noise from eigen vectors. Okay, so from this information we'll be able to separate out the signal and noise component from the eigen vectors. So before we do that, I just wanted to plot out the eigen vectors. Okay, oops, sorry, np dot e vectors. Where is that? Okay, okay, np dot real of this eigenvector. Okay, plot it out. Okay, so this is the eigenvector here, right? And now we need to sort it out. So basically the lowest values will be noise, and the higher values will be signal, right? So we have two signal components, so probably the two of these columns will be fall into the signal region. Okay, so let me do that. So eigenvectors is nothing but we need to take the eigenvectors, and then we need to do a sorting. So np dot arc sort. So basically this is kind of going to sort out the based on the eigenvalues, it's going to sort out the eigenvector. Okay, and once I plot it out, not the plotting, once I show the values, you will understand like how it looks like. And let me write the name of the variable is e vectors sorted. Okay, and also look into the values np dot e vectors sorted, oops, np dot real. Okay, so this portion was without the sorting, okay, and this is after the sorting, and you will see the difference here. So you can see this column comes first, and then comes this column. So these two are the noise, because this has low values, right? And these two are the signal, these two columns. Okay, so we have two signal components. So these two are the columns related to the signal components, and these two are the columns related to the noise, Okay. Also, one thing I didn't do is I calculated the number of signals here. But let's also, just to automate, we need to have also number of noise. Okay. So in this case, the threshold is greater than the eigenvalues. That way, we will get the number of noise. Okay. So we are done with the sorting of eigenvectors, and now we have to take only this noise vector. Okay, because that's what we are going to use in our final form of this equation right here. You see un and un Hermitian, so these are the noise matrix. Okay, and e Hermitian and e right here, this is the steering vector, which is already different. Okay, so we now need to separate the noise. So let's say our variable is qn. Okay, and from eigenvectors, what we're going to do is just going to do some slicing. Okay, 0 to n noise. Since I haven't run it, so it's not popping up, but just going to do it right now. Okay, where it is right here. So let's look into qn. So np dot real qn. Okay, and you can see the first two columns. Oh, okay, so sorry, I have to use this eigenvector sorted, right? Okay, now you can see the first two columns which represent a noise is popping up here. So we have this qn or un in this equation, right? So everything in this equation is already defined. E and e, this is basically the steering vector is defined. So let's implement the music equation. Okay, so we have angle of arrival, let's say theta. Music, the equation which we just showed in the Wikipedia page. So basically we have to have this conjugate, s dot conjugate, complex conjugate, and then transpose. So basically this is the Hermitian, right? You just saw eh right here, right? So that's the Hermitian. Okay, and then matrix multiplication, take the qn, then again multiplied by qn, but the Hermitian. So conjugate, and take the transpose, and matrix multiplication again, and this is with the steering vector s. So this is the equation, and more or less everything is defined. Okay, now we need to do a couple more things here. One is like the field of view. So let's say what are the angles, because the music algorithm doesn't know the answer yet, right? So we have to define some angles where we are going to scan through. Okay, so let's say np dot lin space, and then minus nb dot pi divided by 4. So from minus 45 degrees to plus 45 degrees, and let's say we are going to take 300 points. Okay, I'm just going to silent this line and run this and look into the angles we are going to go through. Okay, but this is in radians, right? So let's say need to convert it into degrees, and FOV right here multiplied by 180 divided by np pi, and let's look into the angles. Okay, okay, so the field of view or the scanning angle starts from minus 45 degrees, and it will have 300 points end up at plus 45 degrees. Okay, and remember we had two target, and somewhere in these angles we have the answers, right? And the algorithm is going to find out what are those angles are. Okay, remember we had the answer should be like 10 degree and 20 degree. That's what we had in the simulation, right? Okay, so let's find out the angles. So this is our field of view, and basically we need to run a for loop here. So for I in FOV, we are going to scan through all these angles. Okay. Okay, and the steering vector equation is missing here, so let's copy it from here. Okay, I'm copying that part and going to paste it right here. Okay, and just going to replace this S1. Okay, so by S. Okay, so this is our steering vector, and Qn is already there, so everything is defined, right? But we are going to have 300 points, and we need to have some container to keep all these values, right? So let's say answers is an empty array right here. So after you use this equation, going to keep the values in answers. So answer dot append, and then you are going to have this theta music. Okay, and let's say since this is a complex number, let's take the absolute value. So np dot absolute of this theta music, and also on top of that, let's take the logarithmic scale. So np dot log 10 of this guy of this absolute value. Okay, and obviously this is a power, so you need to multiply this by 10. Okay, so I think we are all set if I'm not missing anything, so let's run it. Okay, I'm missing something, and I think you also know what I'm missing, because this S is a list, so I have to convert that into numpy array. Okay, and let's run it again, and there is no error, so let's plot it out. Okay, so plt plot, we have the field of view in degrees. Okay, and then we need to have these answers, right? And plot it. Oops, let's run it again from the beginning. So this is a flat line. What is the reason? Because I have not changed this value here. Okay, this is going to be I. Okay, so for each of these angles, we are going to calculate the steering vector and then calculate the theta music. Okay, so you have to be careful. Not like me. I change this. I have to change this to I. Okay, because we are doing iteration here, right? And then let's run it. Okay, so you see two peaks. Let's see what are those angles are. Okay, one thing we can do, we can just normalize it. So do the normalization. We have to subtract the max of answers. Okay, because this is already in logarithmic scale, right? So you do that, and then let's look into only from 0 to 40, because here we don't have anything, right? This is just noise. So plt dot xlim right here, and let's say 0 to 45, and let's also have the grid. So plt dot grid on. Okay, and let's run it. So you can see the algorithm is able to find the two answers. So one target was at 10 degrees and one was at 20 degrees, right? So let's change these angles and see how it does. So let's have one target at 15 degrees go and one at 20 degrees. So you can see like the separation is only 5 degrees now. Okay, it's really closely spaced, and let's see how the algorithm does to find out those angles. Okay, so you see 15 degrees and 20 degrees. However, you can see the noise floor is increased right now. Okay,